Hello, class. Good evening, everybody. Today we only have 9 participants so far. Actually, 10 right now. 10 participants. Yeah, thank you for saying hi. Before we start our lecture today, let's look at the announcement I recently posted in Blackboard. It is about our exam 2. Okay, our exam 2 takes place from October 18th to October 25th. You may take the exam anytime from 18th to 25th, as long as the testing center is open. There are 20 questions only in total in your exam 2, and you have 3 hours, that is 180 minutes to complete them. So you have plenty of time, do not rush. The policies and the rules are the same with exam 1. No book, no notes, closed book, closed note, but you can bring your TID for calculator. There are a few things I want to get your attention. Number 1, please remind me again if you need to take the exam 2 on a foreign testing center. Yeah, I will arrange that. If you do not tell me, then I will not make the special treatment for you. Yeah. So please remind me, even the exam 1, you were taking the exam on a foreign testing center. I don't know if you needed it for the exam 2. Okay. So if you need it, please email me. Second, do not rush the exam. You have plenty of time. The answer choices of the multiple choice question in the exam, they are pretty close, like very similar, worded very similar. So you want to take your time to read them through and get the correct answer. Number 3, pay attention to the rounding instructions in the parentheses. For example, maybe a few questions require you to round the probability to the nearest 10,000ths, keep 4 decimal places. But suddenly you might see a question only require you to round to the third places, like round to the nearest thousandth, only keep 3 decimal places. So you do not make the assumption. You need to read the instruction in the parentheses. Each question is different. Number 5. Oh, hold on. Number 4. If a probability distribution, this is very important, okay? Yeah, very important, this one. If you see a problem and the problem provides you with a probability distribution table, you need to use the information in the table to find the corresponding mean and the standard deviation of the distribution. Even you know the distribution is a binomial or whatever other we have learned distribution, you do not use the formula. You know what I'm talking about? Yeah, so we have learned the formulas. Let me explain what I'm saying here. We do have learned the formulas to find the mean and the standard deviation for a random variable if the random variable has the binomial distribution with n and p. N is the number of trials in the experiment. P here represents the probability of success. And we have learned the formula. Mu would expect the value of x. The average of this distribution is n times p. And sigma, the standard deviation, is the square root of npq. Yeah, we do learn this formula, those formulas. But if the question gives you a distribution table, do not point it out. Even it is binomial distribution, but if the problem gives you a distribution table with those values, and the probabilities 0.123, 0. Something. Yeah, you're gonna use the table. You are not using the formula. Okay, how do we use the table to find the mean and the standard deviation? Use the TI-84 calculator. Enter the first column content in L1, all the possible values for x, and enter the corresponding probabilities in L2, and then use stat calc to find the mean and the standard deviation. Yeah, so this is very important, very, very important. The reason is because if you use the formula, even your answer is actually more accurate, but the system will count it wrong because the system intends you to use the table. That's the purpose of the question. The question is designed to see if you can find the mean and the standard deviation by using the table, not by using the formula. Am I clear about that? Yeah, this part is very important. I hope I got your attention here. Please let me know. You will see when you work on the review. Yeah, you will see similar problems when you work on the review. So knowing if the table is given, do not use the formula. Even formula give you more accurate answers, and the formula can help us to get the answer more quickly. But you don't use it, yeah, because the rounding would be different. Yeah, the system will mark it wrong if the rounding is different. Okay, that's the number 4. Number 5. Yeah, strongly recommend you get a TI-84 calculator and get familiar with those functions. Really would help you plenty, especially binomial distribution, especially normal distribution. Yeah, that probably would make a huge difference in your score. I think whatever the channel, the method you have, either borrow or buy or purchase, it's worth the effort to get a good calculator to be with you, okay? Take it with you to the exam. And that's the first thing. Read the announcement about the exam 2, all right? Time and the location, the requirement. Second thing, just now, I sent you an email, okay? I don't know how many of you and how often you look at your email. I included myself in the recipient, so I should have the email as well. Let me show you what's the email talking about. The email is about our review class next Tuesday. Today we plan to finish 6.4 and 6.5. On Thursday, we want to finish or cover 6.6, the last section of this chapter. And then next Tuesday, in a week, we are going to review for test 2. Yeah, for review test 2, the review has 28 questions, and some of them pretty time consuming. So if we take our time to go over each single of the questions, 80 minutes would not be enough. So here I want you to participate. I want you to email me the questions that you need help with. Yeah, of course you need to do your review first, right? At least take a glance. Yeah, knowing I know this question, I know how to do this one, but I do not know this one. Yeah, maybe I would ask the instructor to cover this question in the review session on Tuesday, which is October 17th, right? Yeah, here I emphasize, please respond this email by replying all. The reason I want you to do this because other students, your classmates would be able to see what questions are already there, are already requested, right? Yeah, you can agree, okay, I need that question too. I have a problem with that question too, but you don't have to post it again. If you post it again, you probably maybe the number is different, but would be the same type of a question. We don't want to do the same type of question twice. All right, yeah, do that before we start within a week, within this week, the next week, before our meeting on next Tuesday. All right, is that clear, guys? The second thing. Sounds good. Okay, awesome. Perfect. Very good. Yeah. And then with 17, we review for test 2. And then from 18th, you have 1 week to plan your exam 2. And after 17, we're going to meet on 19. So we're going to start chapter 7. Yeah. Estimation. Okay. So let's start our lecture today. Today we want to cover 2 sections. Central limit theorem and how do we assess normal distribution or evaluate normal distribution. So this is section 6.4 and we're gonna also cover 6.5 today. Okay, section 6.4 is about the famous central limit theorem. The famous central limit theorem. What's the content of a central limit theorem? What does this theorem tell us? Central limit theorem says if we have a population X, regardless the distribution of the population, it doesn't have to be normal. Yeah, it could be any type of distribution, regardless of the distribution of the population. As long as the sample size, yeah, we got a sample from the population. As long as the size of the sample is bigger than 30, and that's not difficult to meet. Yeah, that condition is not difficult to meet. 30 is a pretty small number, to be honest. But as long as the sample size is bigger than 30, then the sample means, yeah, those sample means, we're gonna use X bar to represent all the sample means. Okay, yeah, we have a population. We are able to get many samples from the population, and we want to keep all those samples the same size n. As long as the size n is bigger than 30, then those samples, their sample means are gonna be roughly normally distributed. All right, yeah, let me explain this variable. This is a variable because I use a capital letter X and put a bar on top of it. That means this variable represents all the sample means with the size n from the same population. Yeah, so we have one population X. It has many values. Yeah, very large population normally. And we're gonna take many samples. We want to keep those samples the same size. Let's say size n. Well, as long as those the sample size n is bigger than 30, then the sample means, yeah, from each sample we can calculate the mean. So we got a sample mean. Since we have many samples, we have many sample means, and those many sample means can be represented by this variable. Then that variable is roughly normally distributed. And the mean of this variable is the same with the population mean. And the standard deviation of the normally distributed variable, actually roughly normally distributed variable x bar, is the population mean divided by root n. It is actually smaller. And the reason is because it's kind of like smooth. When you take the average, you smooth the values. You lower the variation. Okay? Yeah, I just give you a gist or idea about what is central limit theorem. Let's identify some notations involved in central limit theorem. Firstly, I use X, capital letter X, to represent the population, and assume the population has mean, mu, and the standard deviation, sigma. They are parameters, right? Parameters correspond to population. Yeah. And we use X bar, capital letter X bar, to represent all the sample means of samples with the same size n from the same population X. Yeah. We focus on the distribution of this guy. We focus on the central limit theorem is about the distribution of this guy. Sample means, they represent the sample means, all the sample means with the same sample size and from the same population. Okay, how do we actually apply a central limit theorem? Another version or more useful version of central limit theorem is this. Okay, so if we have a population, if the population satisfies the following one of the following two conditions, it doesn't have to satisfy both, at least one. Okay, here or is inclusive or, yeah. If the population is normally distributed, then its mean of course is normally distributed, no problem. But if the population is not normally distributed, it's fine. As long as the sample size is bigger than 30, the sample mean is still normally distributed. Is that clear about the content of the central limit theorem? The central limit theorem is about the distribution of X bar, capital letter X bar. It is a variable that represents all the sample means of samples with the same size n from the same population X. Turns out, as long as one of the two conditions are satisfied, and that variable is normally distributed, which two? Either the population is normally distributed, or the sample size is bigger than 30. Yeah, one of the two conditions is met, would be enough for us to draw the conclusion that X bar is normally distributed. Not only we know X bar is normally distributed, we also know how to find its mean and standard deviation. Then we can find the probability of X bar fall in certain interval. Okay, please let me know, am I clear about the content of the central limit theorem?
I have a question for X bar. Why is the standard deviation divided by the square root of n?
That's a very good question. That sigma is the population standard deviation. It is bigger than this value. Because when we take the average, when we have a bunch of numbers and we add them up and divide by the sum by the number of the values, we smooth the value, right? We kind of smooth the value and we make the variation smaller. And you want to know why it's divided by root n. I can explain why it's smaller than sigma. To explain why it's sigma over root n, that takes a lot of formulas.
That's okay. It's sort of used to help smooth it over because it's such a big number is sort of what I understood.
So let's say we have many values. This is real number line. The population has many values, big variation, right? When you take a sample, you randomly take a sample, and you take the average, you get the first sample mean, and the average is going to be in the center, right? And you get another sample mean. That sample mean is in the center. So x1 bar, x2 bar, those sample means would have a lot less variation than the original population values. Because when you add them up and divide by the number of values, when you take the average, you smooth it out. Does that make sense?
Yes, that's great. Thank you.
For your question, why is it divided by root n? That takes a lot of formulas. And we don't even learn the density curve. So I can answer your question later with the formulas. All right? But here the sigma over root 10 definitely is smaller than sigma, because the sample means are when we take the sample mean, when we average the values, we reduced the variation. Okay, so let's look at some questions that about the content of the central limit theorem to reinforce what we have learned. All right. Number one, what tells us that a population with any distribution, the distribution of the sample means approaches a normal distribution as the sample size increases? Which theorem tells us that? Roughly normally distributed kind of says the same thing, right? Approaches, yeah, the sample means approaches a normal. Which theorem? Central limit theorem, right? Yeah. The whole section 4.6.4 is about the central limit theorem. Number two, the standard deviation of sample means is what? Is sigma over root n. Sigma is the population standard deviation, n is the sample size. It is smaller than sigma, and why it is root n, it takes a lot of proof. When I was in China, I have taught probability and mathematical statistics. It is different from our statistics, because mathematical statistics mainly is about a proof. Use integral to prove the probability conclusions. So I knew why is that, but it takes a lot of work to prove, to show you why is that. You know what I'm saying? Yeah, and for us, we only need to remember is sigma over root n.
Yes, and that makes sense. So I guess the important word here in that sentence is distribution. So the distribution sort of makes it sigma over the square root of n. Is that correct?
The distribution makes a sigma over root n. Can you repeat what you said?
I'm trying to find the key words in order to know what formulas and stuff to use for things. So it seems like distribution is the key word for this compared to, I don't know, bias and unbiased for the last chapter.
Biased and unbiased is the estimator.
Yeah.
The key word for sigma root n is a standard deviation.
Okay.
Yeah, that's the key word. What is this? This is a notation of what? Notation of standard deviation. Standard deviation of what? Standard deviation of x bar. What is x bar? X bar represents all the sample means with size n from the same population. All right.
Okay, thank you.
Okay. Yeah. So in my country, in order to take the mathematical statistics, you have learned calculus before that, because mathematical statistics takes a lot of integral calculus stuff to prove those formulas. We don't need that. We only focus on how to use them and understand the concept. Number three, which of the following is not? Yeah, sometimes we really need to pay attention to the question. Yeah, which of the following is not a conclusion of a central limit theorem? You know what? I forgot to cover those answers. Okay, sorry about that. Read ABCD. Yeah, pretend this is a problem on a test. Yeah, which one you should choose? Especially when you after you this part, choose the correct answer. Choose the correct answer. But actually, you are choosing the one which is not a conclusion, right? So be very careful. You know the logic here. Yeah, A, the mean of all sample means is the population mean mu. That's correct. That's correct. B, the distribution of the sample data will approach a normal distribution as the sample size increases. So here, sample value, sample data. I don't think so. Yeah. So those values, the values from population would be the same with the population distribution. No theorem guaranteeing they approaches to normal distribution. This one is incorrect. C, standard deviation of all sample means. Yeah, we are talking about sample means. Is the population standard deviation divided by the square root of n. Yeah, that's correct. That's correct. D, the distribution of the sample means will, as the sample size increases, approach a normal distribution. That's correct. Yeah, that's correct. So that's why we have to ask n is bigger than 30. Yeah, as long as n is bigger than 30, of course, the bigger the better, right? Yeah, but once n passes 30, then the sample means would be roughly normally distributed. Even it's not strictly. Yeah, the distribution would look like you know, a bell-shaped curve, symmetric, yeah, would be roughly normally distributed. So this one we should choose B. So once again, you can stop me anytime and ask question. All right? Yeah, I appreciate your participation. Yeah. Otherwise, I feel like I'm talking to myself, especially the online live class. I'm sitting in my own study and I don't see anybody. If I don't hear you, sometimes am I talking myself? Am I just recording the videos? Number 4, which of the following is not a commonly used practice? Choose the correct answer below. A, the distribution of sample means gets closer to normal as the sample size getting larger. Yeah, that's exactly what the central limit theorem talking about. So this is correct. We do not choose it. B, if the distribution of sample means is normal, yeah, if the distribution of sample means is normal, and n bigger than 30, then the population is normal distribution. I don't think that's the thing. Yeah, it's the opposite. The order of the statement is false. Yeah, this means incorrect. Okay, incorrect. There's no way you can know what the population distribution is by looking at the distribution of sample means. Okay, because even the population is not normal or any other type of weird distribution. As long as the sample size go beyond 30, then the sample mean is always roughly normally distributed. So B is incorrect. Let's see what happened to C. If the original population is normal and is not normal and n is beyond 30, then the distribution of sample means can be normal. Yeah, that's correct. Okay, regardless the distribution of the population, most important is the sample size, because that's what we can control. That's what we can control. We cannot control the distribution of the population. It is what it is, but we can control the sample size to make it bigger than 30. That's not difficult to do at all. And part D, if the original population is normal, then the sample means will be normal as well. Yeah, for sure. That's for sure. Okay, that's for sure. If the original population is normal, then each value would be normally distributed And when you add them up and then divide by n, we keep the normality. Yeah, there's also a theorem to support that conclusion. Yeah, the normality remains. So this basically, this is the first value, second value, because all of them are normally distributed. The sum of them also normally distributed, and you divide by n is also normally distributed. So the sample means is normally distributed. So if the population is a normal distribution, then of course the mean, sample mean is also normally distributed. Number 5, a researcher collects a simple random sample of grade point averages of statistics, so GPA. As she calculates the mean on the sample, under what conditions can that sample mean be treated as a value from a population with a normal distribution? So this is about application of central limit theorem. So two conditions, right? Either the population is normal or sample size bigger than 30. So that's exactly the two conditions I mentioned earlier, one or the other. Not one or the other, at least one of them. Yeah, sometimes they both satisfied, even it's not necessary. Sometimes they could be both satisfied. Of course, that of course guaranteeing a normally distributed sample means, variable sample means. Yeah, so those two variables, at least one is satisfied, then the central limit theorem conclusion will be true. Number 6, weights of golden retriever dogs are normally distributed. Samples of weights.
Sorry, going back to the last problem, number D, or letter D, excuse me. Going back to the last problem, letter D, the researcher collects more than 30 samples. Why is that one not valid? Because it's 30N, right? Or
that's a very good question. Yeah, that's a very good question. Yeah. So the requirement is n bigger than 30. And 30, the n is not the number of samples. N is number of sample size, is the number of values in a sample. Yeah, that's a very good question. For your participation. Yeah, most of the students don't see the difference. Let me explain again. N here is the sample size. It is the total number of values in the sample. So we get many samples, right? And all those samples have the same size n. The number of values in the sample is n. Is different from saying the number of samples. You know what I'm saying? D is researcher collects more than 30 samples. But what if each sample only have 2 values? That would not work. You see what I'm talking about? Hello?
Not quite. Can you give another example?
Oh, okay. So let me do it again. So what if the researcher collect more than 30, let's say 31 samples, and each sample only has 2 values? That means the sample size of those 31 samples is 2 only, is far less than 30. So the central limit theorem will not be hold. Still not clear?
I think so, but can you give like a real world example? So like, let's say you have 31 students and you're getting 2 grades to make their GPA. Is that sort of how it would work for this specific example?
Okay, can you explain what your understanding about n? What is n in your understanding?
The number of trials, I guess? The number of things.
So it says sample size, right?
Mm-hmm.
Yeah, n is the sample size. Can you tell me your understanding about what is sample size? we know
number
what
of
is the
samples.
Oh, no. Sample size is not number of samples. No. Sample size is the how big the sample is. Okay. So let's say we have a population. Yeah, your scores. Okay. Population is your scores. Yeah. And then I want to collect one sample only. Okay. One sample. And I want to determine, of course, I need to determine how many values I need to get from the population, right? Yeah, I can get two scores. Then the size of the sample is 2. You see what I'm talking about? No? So
sure, I think, but we can move on and I could get with you
I want
later.
to make it anyone can help me here that differentiate between sample size and the number of samples.
So 2 scores will equal 1 sample, correct?
Yeah, 2 scores make one sample. Yeah, 2 scores make one sample. That's my first sample. It has 2 values. So that sample size is 2. Exactly. I can get another sample. My second sample, this time maybe I collect 10 values. Then my n is 10. The size of the second sample is 10. Does that make sense? Better? No?
Yes, I believe so, but it'd still be helpful to sort of have like a real world example. Like I guess, like let's say you're taking a person's temperature. So like it's the sample is for one person and you take it like 10 times. Is that what you're talking about? And like then another person's temperature and you're taking it only twice. Is that sort of how they're different? Is like the sample is the person and then the numbers are n?
Let's use the temperature. So let's say X is the population, represent your guy's temperature. So at this point, I'm gonna measure everybody's temperature, right? So in this case, my population. So how many of you right now we have in the class? We have 12 students. We have 12 students, so my population is gonna have 12 values: x1, x2, x3, all the way to x12. That's my population, right? Yeah, that's my population. Now I want to get a sample. My first sample, I'm going to randomly select 5 people and measure them. So I would have 5 values here. Let's say 98. I don't know the temperature. I just randomly write the numbers. Okay. Yeah. So those are the 5 temperatures I got from the population. Then tell me what's the size of this sample. What is the size of the sample?
Okay, that makes more sense. But yes, it's an N5 sample size.
Yeah, size is 5. Our n is 5, right? But we only have 1 sample so far. I'm going to keep getting more samples. I can get 100 samples. Yeah, that's 100 trials. My one trial is to get 5 people and measure them, right? And I can get a sample 2, the second sample, third sample, fourth sample, all the way to the 100th sample. So the number of samples in this case is 100, but the sample size for each sample is 5 only.
So because for this one, the sample size is only 5, you wouldn't be able to do the central limits theorem because it's not large enough.
No, you can't. Yeah, you're right.
Okay.
Hold on. You could, because temperature in fact is normally distributed. Yeah, temperature in fact, the population is normally distributed. Okay, at least one of them satisfied would be fine. Okay. Yeah, I mentioned before.
Okay, that makes sense.
I mentioned before, how do you know which variable is normally distributed? And you just mentioned normal distribution is very popular in real world. Many things are normally distributed. Yeah, how do we know it is normally distributed? Is also actually could be proved. Yeah, so if we have a population variable, and the variable is the combination of many small factors, and all the factors will contribute to the variable, but none of them is dominating, then the variable is gonna be normally distributed. In real world, like temperature would be one of this type of variable. Yeah, your body temperature is like a DNA related thing. DNA related thing, your weight, your temperature, your height. Yeah, those things. Your arm circumference. Yeah, those sort of thing has many factors. Depends on many factors, right? Environment, like genetics. Yeah, you can even say it or make a list, and those factors all contribute, but none of them is dominating. And so those kind of variables is normally distributed. Temperature is body temperature, by the way. Body temperature is normally distributed. It means in reality, majority of the people's temperature is around average. There's only small proportion their body temperature is pretty high, and there's only small proportion people their body temperature is low. Yeah, another example, like a height. Yeah, in real world, just by observation, majority of people their height is around the average, right? Not too high, not too low. It's always like that because we have so many people. Yeah, you would see, when you see a very tall girl, oh, she's so tall. When you see a very short girl, oh, she's so short, right? You have this judgment based on the common sense. Only small proportion people very tall, very tall, significantly tall. Very many a small percentage of people pretty short, significantly short. That kind of thing are normally distributed. Okay, like salary is the same. Yeah, normally the people's salaries are around this, averagely that. Only small portion people very rich, very high salary, and only small portion of people they are very poor, very low salary, right? Kind of like that. Did I answer your question?
Yes, that helped me understand what the variable or what the different symbols mean. Thank you.
Exactly. Difference between number of samples and the sample size. That's very good. I enjoy the conversation. Yeah. Okay, so number 6. Did we do that one? Normally. Okay. Did we do number 6, guys?
No, we have not done number 6.
Okay. Weights of golden retriever dogs are normally weights, right? Normally distributed. So population is normal distribution. Samples of weight, each size. Yeah. Now you get a sample. Now you get samples with a size 15. 15 is less than 30. Yeah. 15 is less than 30. So is it correct to conclude the sample means cannot be treated as normal? Can we say that central limit theorem does not work in this case because the sample size n is only 15, is less than 30? We can't because the population is normal, right? Yeah. So again, 2 conditions, at least one of them is met, then the central limit theorem conclusion will be true. What conclusion? The sample means is normally distributed. Yeah. So here, since the original population is normal distribution, so it doesn't matter the size, the sample means are also normally distributed. All right? Okay. So next, a few questions gonna involve those 2 things. Okay. Yeah. For calculation, not multiple choice question. Yeah, I want to get your attention on that. So either the question asking you to calculate the probability of an individual value, about an individual value from the population, then in that case, yeah, I want you to write it down. You're going to use the calculator and use the function normal CDF with population mean mu and the population standard deviation sigma. So the difference is here. And if, yeah, other questions requires you to find a probability about the sample means, okay, sample means, then in that case, once the central limit theorem is satisfied, central limit theorem, yeah, suppose the central limit theorem is satisfied, then you can use the normal CDF, but this time you're going to use the mu as the mean and the sigma over root n as the standard deviation. All right, yeah, take a quick picture of these two things. Very important thing is the first one, the yellow one, you are actually using the population distribution as I shown you here, this curve, yeah, this arrowhead. Yeah, this is just one value from the, yeah, if you are considering the probability of one value from the population fall between a certain interval, then actually you are concerning the distribution of the population. That's the reason your parameter are mu and sigma. But if you are looking for the probability about sample means, then you are actually considering the distribution of x bar. In that case, you're going to use those two as the parameters. All right? Yeah, so let's write it down or take a quick picture or screenshot. Yeah, very important. Yeah, the difference is very important. Okay, let's practice the one I circled here. Yeah, this one. So number 7. Let's read through. Those questions have a lot of words, then you do need to take time to understand them very well. Okay, let's read it. The overhead reach distances of adult females are normally distributed with a mean 205.5 centimeters and a standard deviation 8.6 centimeters. Yeah, what is that? Reach your arm, overhead reach distance, overhead reach distance. So I think it's the distance between your head, top of your head, and no. So it is from the floor to the tip of your finger when you reach your arm. Overhead reach distance. Yeah, that's why it's over 2 meters. Yeah. Okay, anyway, that is our population, okay? That's our population. And the population is normally distributed with mu as the mean, sigma with the standard deviation. Yeah, that's that sentence about. Mu and sigma are given. Part A, find the probability that an individual distance is greater than 208.9 centimeters. Okay, part A, we are looking for probability that an individual distance is a value from the population, right? Yeah. So actually, it means the probability of the reach distance, overhead reach distance, bigger than 208.9. That's the probability. Sorry, that's the probability we're looking for. Do you guys agree? Yeah, one of the values, one value of x, that value is bigger than 208.9. That's pretty tall. Yes or no?
Yes.
We can totally use the variable to represent an individual value. Yeah. So it actually doesn't make any sense if we use the little x, because little x is a certain value. You really cannot actually, it really doesn't make sense. This is not random variable. You would have to use the variable x to represent that individual value. Yeah, the variable x, the population represents the individual x. So we are looking for p of x bigger than that. Okay, yeah. How do we do that? Is not difficult. If you have a TI-84 calculator, okay, get your calculator, please. What's the distribution of x? Isn't that given? It's normal, right? Yeah. For normal distribution, we are looking for probability. What's the function we need to use? Normal CDF, guys. Go to second verse and look for normal CDF. Yeah. And then you're going to enter the lower. And since x is bigger than 218.9, the lower is 218.9. The upper, I'm not going to show you my calculator today because I already feel the system is very slow. If I change back and forth my document camera, it would only slow it down. And this is not new. I have shown you many times this. So your upper is gonna be E99. Let me know if you don't know how to enter E99, okay? The E you need to have is actually double E. You just need to enter second, push the button second and a comma, okay? Yeah, second comma would give you the double E, and you enter 99. The mu is given 205.5, sigma is given 8.6, and then you calculate. Let me see what's the last one. Probably is paste. Yeah. So we go to second verse, normal CDF. Yeah, lower, upper, mu, sigma, paste. Let me know what you have, guys. Yeah, the lower is 218.9. You also have to have some understanding about the inequality. Okay, this inequality is equivalent to x is bigger than 218.9 and smaller than passing infinity. That's why your lower is 218.9, your upper is passing infinity. Okay, so keep 4 decimal places. Yeah.
Yeah, on mine, I left, because I did it before you did the example, and I left the lower the exact same. I left the lower at -1 E99, and I did the upper at 218.9, and it came up with the 94 point whatever, and then you subtract a 1, and it actually came up with that answer, 0.596.
Is that the same thing?
Yeah.
Yeah, of course. What? Yeah, it's destined, right? What you actually found is x is less than 218.9. That's the probability you found, and those two events are complement. All right. Yeah, x is less than 218.9 is a complement of x bigger than 218.9. It really doesn't matter the equal or not equal. Same thing because it's continuous. Right, Dustin? Yeah, that's why you have to subtract that from 1.
Yeah. So both ways actually work. You just have to remember to subtract the 1 on the final answer if you do it the way I did it.
Yeah, both work, but I would prefer you as long as you understand the probability you got, the relationship between the probability you got and the probability you need to enter, you need to find. Yeah, if you know the connection, yes, no problem. All right. Okay, let's see. Miranda have a message here. Oops. Never mind. How do you do? Okay, Charlene said, how do you do E99? That's a very good question. On your calculator, enter second. This key, you see this key on my calculator is blue. No, yeah, it's blue. Yeah. second comma, there's a key comma. Actually, if you look closer, super tiny, above comma, you have two things, right? Yeah, I need to turn on the flashlight in order to see that. Yeah. So above comma, you have double E on the upper left corner. Upper left is in blue, and you also have a J is in green, right? But we don't need a J. We need the blue double E. So you have a second comma. Enter second comma, you would have double E. But on the screen, you would only see one E, one capital E. And you enter 99. Charlene, did I answer your question? Okay. No problem. And Miranda say, never mind. Okay, let me see any other things I missed. Okay, your answer is 0.0596. Yeah, that's correct, guys. You guys great. Yeah, you need to figure that out. You want to pass exam 2, please figure that out. Okay, yeah. I would not recommend use the table, even table is given by the system when you take the test. It's too troublesome. You have to standardize it. I don't think you like to standardize it. Okay. Anyway, so that's part A. Part B, find the probability that the mean, look at here, the mean for 20 randomly selected distances is greater than 203.30. Okay. So here the mean is bigger than, so we are looking for the sample mean, okay? Because the sample, right? Sample mean is bigger than 203.3. Do you guys agree? So part B is looking for the probability of the sample mean. Yeah, this variable represents the mean for 20 randomly selected distances. Yeah, first we need to agree on that, guys. Do we agree on that? Let's see. So obviously it says not the population, is the sample means, right? Okay, you already got an answer. Hold on, let me scroll down. Yeah, you understand that. Perfect, is clear. And however, the sample size is only 20, is less than 30. Then can we use the central limit theorem, guys? Can we?
Yes, because it's normally distributed numbers, right?
Yeah, population. Yeah, the population is normal, right? Awesome. What's your name again? I couldn't see who is talking here.
It's Callie Burgess.
Oh, Kelly. Awesome. Exactly. Thank you, Kelly.
No
you
problem.
are right. Yeah, the sample size doesn't matter as long as the population is normal. And in our case, the weight of the dogs, they are normal, right? So totally fine. We can use the central limit theorem. Okay, so that means the lower is gonna be 203.3 and the upper is gonna be past infinity. In your calculator, okay, let's do the calculator, guys. Go to second verse, select the function normal CDF. The lower, you are going to enter 203.3. The upper, you are going to enter double E 99, but you only see one capital letter E 99. And your mu, yeah, who can tell me what's the mu? Yeah, you can see it. Yeah, 205.5, right? Yeah, this is actually faster. For me, like your mu is 205.5, right? Same with what is 20? Not 20. Kayla says no. Kayla, can you specify which part you need help with?
I got it now. Thank you.
Okay, awesome. Yeah.
Or I understand.
What about Miranda? Can you specify the question that you need to be answered? That need to be answered. What is 20? 20 is the sample size. Yeah. I was asking what's the mu? Mu is the population mean. So we agree the central limit theorem works. So we're gonna use the normal CDF, right? Because X bar is gonna be normally distributed. And when we use the normal CDF, we need to determine the mean and the sample standard deviation, right? I'm sorry, not standard deviation, just standard deviation. So the mean is going to be same with the population mean. So you're going to enter 205.5, but for the standard deviation, very, very important, I need your attention. It's going to be, is not 8.6, it's going to be less than 8.6. You need to divide 8.6 by square root of 20. That's where do we use the value 20. Yes or no? So here,
are you actually able to do that calculation inside of it, or do you need to like do it and then like input it?
Oh, that's also a good question. I do not do outside. I just do this. I do 8.6 and enter divided by, and then I use the square root and enter 20. I think some question has some calculator require the parentheses, so I just close the parentheses. I don't do like a second mode and go to the main screen and calculate that part. I calculate it right there. Yeah, 8.6 divided by square root of 20. Square root is on the calculator is above x squared. Yeah, let me see the question here. You must know this, guys. Yeah, Melinda has 0.87. Yeah, correct answer. Melinda gets the correct answer. Very good. Very, very good. Yeah, I want to make sure everybody do. Can you specify your question? Which part you need help with? Miranda, could you tell me the specific thing that I need to help you with? I understand now. Okay, awesome, very good. So you know this section, when you do your homework, I don't really worry about those multiple choice questions. You just figure out, you can figure out yourself for sure. What I need to do, then you do not struggle when you do your homework, is I need to make it clear. Some question like this. Part A is about the probability of X. Part B is about the probability of X bar. When X is normally distributed, it doesn't matter the sample size, X bar is also normally distributed. Mu means mu, and the standard deviation is sigma over root n. That's what the central limit theorem says, right? Yeah, that's exactly what the central limit theorem says. So we're looking for probability of X bar bigger than 203.3. So the lower is 203.3, upper is passing infinity. Sample mean, sorry, not sample mean, my bad. Mean is 205.5. Standard deviation is the population standard deviation divided by, yeah, this part is super important. Knowing sample mean has a smaller variation, you have to divide this population by root 20, make the number smaller. All right, I want to make sure everybody understand this. I want to make sure everybody understand this.
I have a question.
Yes, please.
So on the calculator where it says lower and upper, lower is, so like A says find the probability that individual distance is greater than 218.90. To know that, to put that in the lower section is because it's because the wording on the A part says greater than 218, right? On the bell curve.
Bell curve. Okay.
Does that make sense?
So the bell, yeah, this is the bell curve. Center is 200-ish. So center is 200 is 200-ish, 205.5. So we are looking for the probability that X bar is X bar. Yeah, is bigger than 203.3. So it's gonna be around here, a little bit less than the mean, from here to infinity.
Okay, so we're looking for that part, so that's why we're putting the lower as the 203.3.
Yeah.
Okay.
Yeah. So this region is from 203.3 all the way to infinity, right? Horizontal, on the horizontal scale. Yeah. So yeah, it's good that you see the graph to understand it. Well, if we use algebra, if you remember algebra, this inequality X bar bigger than 203.3 is the same with 203.3 is less than X bar. The inequality symbol like alligator, greedy alligator, right? Always chasing the bigger quantity. And that's also the same with less than infinity. So those two inequalities are equivalent. Yeah, that's how do we know this is the lower bound, this is the upper bound. Yeah, this is the lower, this is the upper. Yeah, but you just point out a better strategy is you graph it, and you can clearly see is that the region is from 203.3 all the way to infinity, and that helps you to find the lower bound and upper bound as well. Did I answer the question clearly, guys?
Yeah, thank you.
No problem. Yeah, I use algebra a lot, but actually I really think the graph would help plenty. Okay, part C, choose the correct answer below. Yeah, part C is right here. We need to read it. Why can the normal distribution be used in part B, even though the sample size is not bigger than 30? Because the population is normal, right? Yeah, we have seen that a lot. Yeah, again, from the very beginning, I already pointed out the two conditions of which at least one is satisfied, then we can conclude the sample mean is normal. Yeah, the two conditions is the first one is normal population. Population is normal. Second one, sample size bigger than 30. Yeah. As long if this is correct, this doesn't matter. It doesn't matter. Yeah, as long as at least one is met. Okay, let's one more. Okay, let's do one more. One similar with number 7. The one I circled. You see the table. I don't really use those tables. That's number 7. This is let me see what is in number 9. Okay, number 9 is good. Candles. It's good because it's easier to read. Some other questions, a lot of background. Okay, this one. The weight of a certain brand of candies are normally distributed. Okay, so that means the population is normally distributed. And the mean and standard deviation is given. Mean is given. This is mu. Standard deviation is given. This is sigma. Yeah, those numbers are small because it's a candy, right? Yeah, how much weight candy could it be? Just very tiny. a sample of these candies came from a package containing this many candies. Okay, that's our sample size. 450. Yeah, when you see a sample size that big, it really doesn't matter the population distribution. Yeah, it doesn't matter is it normal or normal. In this case, it's normal. But even it's not normal, doesn't matter because the sample size is so large. Yeah. The package label stated that the net weight is 383.9 grams. If every package has 450 candies, the mean weight of the candies must exceed 0.8532 grams for net contents to weight at least 383.9. Okay, a lot of information. Yeah. So there we have a claim here. Just see, we have a claim here. The package weighed that much. Okay, part A. If one candy is randomly selected, find the probability that it weighs more than 0.8532. Okay. Again, we see the individual, right? One candy. One candy is selected. Which variable represents that one candy? That one candy could be any candy from the population. Yeah, so this is about the population. Yeah, the probability of population is bigger than 0.8532. Okay, yeah, part A has nothing to do with the sample. Yeah, X. Thank you, Kelly. Exactly. Okay, so when we go to calculator, yeah, go to second verse, use the normal CDF. What is your lower? What's your upper? What is your mean? What's your standard deviation? Yeah, those are 4 things. Your lower is going to be 0.8532. Your upper is going to be double E989. Your mu is going to be 0.8576, which is given. Your sigma is going to be 0.0515, which is given. And then you paste. All right. Yeah, please work on that and let me know. Do you have the same probability with me? So that is about the probability of one individual. 5340. Awesome, exactly. Yeah, thank you, Charlene. It's the same. Yeah. All right, that one is, I don't think that one is challenging. Yeah, they put them together, then you can differentiate the 2 probabilities. They are about 2 different variables. Okay, part B. If 450 candies are randomly selected, that's a sample. That is sample with size n equals 450. Yeah. Find the probability of their mean. Okay. You see that? One sample mean. And that one sample mean can be represented by X bar, right? Yeah. The sample mean is at least, okay, you have to be able to translate those keywords correctly. At least means bigger than or equal to 0.8532. Okay? How do we find that? Since the sample mean is so large, well, actually also because the population is normal. It doesn't matter. Yeah, in this case, both of the 2 conditions are satisfied. Yeah, of course, central limit theorem is applies here, right? Applies here. So X bar here follow normal distribution with mean mu and standard deviation sigma over rho n. Okay, let's see if we go to calculator and we use the normal CDF. How do we find the lower? How do we find the upper? How do we find the mean and the standard deviation? All right. Okay, what is lower? X bar is bigger than or equal to 0.8532. So this number is the lower bound. Lower bound. So your region is going to be to the right of the value. So that is the lower bound. Your lower bound is 0.8532. Yeah, you also need to sure you can find the lower and upper correctly, especially if you are not very familiar with inequality, like algebra thing. You need to work on that, okay? And your upper bound, there's no upper bound. There's only one lower bound at least, right? There's no at the most. So your upper bound is past infinity, so E99. Your mean is the same with the population mean. Yeah, why? Because of what? Because of the sampling distribution. Yeah, we went over sampling distribution when last time? Yeah, sampling distribution because of that. And the sigma, very, very important here, is going to be the population standard deviation 0.0515 and divided by rule 450. Make it smaller, make it even smaller. 0.0515 divided by rule 450, square root 450. Okay, tell me what do you have? What's your probability? Yeah, those two numbers are the same. You can really feel it's a very good question. Yeah, what's the probability an individual can be bigger than that value? And what's the probability the average of the package is bigger than that? Yeah, this probability is going to be bigger, right? Yeah. Do you have the 0. Yeah, exactly. Thank you, Kelly. Thank you, Destin. Yeah, thank you, Charlie. Yeah, is bigger than. Yeah, why do you think it's bigger than that? Because when when the standard deviation is smaller, yeah, this is the curve of x. Curve of x bar is going to be this, like this, because it has a smaller variation. So region-wise, let's say the region, what's the mean? 0.85. So a little bit sorry, a little bit less than the average. Yeah, this is the center. This is center. This is center. Our region start from a little bit less than the center. Yeah. So the region here, you see, this is the region, and this is the region. The probability is bigger because this curve is taller. It has smaller deviation, smaller variation. So the region is bigger. You know what I'm saying? Yeah, the same value from 0.8532. This is also 0.8532. It has more region here. Area is bigger. Okay, very good. I think that's everything I want to cover in this section. I actually planned to cover 2 sections today, but we only did 1 section. Next but am I clear about the only 1 section? Central limit theorem is very important. Since it's so famous, after we finish this course, and if people ask you what is the central limit theorem and you are not able to explain it, that kind of sucks, right? Yeah, I would prefer you really understand what is central limit theorem. It is about the distribution of sample means. Okay, any questions today? So next time I would have to cover both section 6.5 and 6.6. And 6.6 takes a little bit of time. Any question, guys, for today? We finished the 8:50, right? Let me take a picture of the attendance. We have 12 participants. If you have some simple questions, like not very time consuming, you can stay and then ask me. if the question is time consuming, I would like you make appointment with me and we work on that. It's only because our class is so late and kind of already exhausted from the whole day working. I understand. Thank you for all the. Okay, thank you, Kayla. All right, guys, I'll say good night. I'll see you on Thursday.